let's kick it off with on YouTube. We'll just give me a shout, Clara, when we're ready.
Yeah, we're live now.
All right. Hi, everyone. Thank you for joining us again for another set of talks and in this block, which will focus on state measurement and state transfer. So today we're really lucky to have Michael Vanner from Imperial College London giving us a talk. But before I introduce our speaker for today, just a quick update, of course, house rules. As you're all now well aware, if you have any questions, please type them in the chat or you raise your hand at the end. And if you're joining us through YouTube, feel free to, of course, put anything you'd like in the chat. And the team will pass it on to myself to ask Michael directly. Okay, so without further ado, I'd like to introduce you, if you don't already know who Michael is. He's a principal investigator in the quantum measurement lab, and his research interests predominantly span both in experimental and theoretical research foundations of physics, and also looking at new quantum technologies. He's the recipient of the UKRI Leadership Fellowship, Future Leaders Fellowship, and also the Australian National Measurement Institute Prize for his outstanding contributions to precision measurement in emerging new fields of cavity quantum optomechanics. Although I'm very excited to have him, and of course we are always grateful for Michael in the past as well. So without further ado, Michael, the floor is yours.
Oh, Modesta, thank you very much for that kind introduction, and really excited to be here today. And also good afternoon to everyone tuning in to this talk, be it via Zoom or via the YouTube stream. And this afternoon it'll be my great pleasure to discuss with you some of our recent experimental results in our team, the Quantum Measurement Lab here at Imperial College London. Excuse me. And in particular, this afternoon, I'll be describing some of our experimental work in Brillouin optomechanics in whispering gallery mode resonators. And I'll be discussing our demonstration of this, achieving the strong coupling regime with this platform, and also some operations that are exploring single-phonon level manipulation to these acoustic states. And I'd like to add another big thanks to Modesta and indeed all the Unicorn team on behalf of our team here in Imperial College, our labs in the basement of the Blackett building. The team and I have been really enjoying both tuning in to these Unicorn talks as well as contributing. I'm very happy to make a further contribution to the series this afternoon. Thanks again, Modesta. And I have the great pleasure of working with a bunch of students and postdocs in our team. And together we pursue a combination of experiment and theory in quantum optics with a current focus on quantum optomechanics. And at the moment, we're very interested in the basic quantum science that underpins near future quantum technologies such as quantum sensing or quantum information applications, and also the basic quantum physics that can underpin near future experiments that test the very fundamentals of physics in a tabletop style experiment. And this slide here isn't really necessary in this great series of talks, but if you are unfamiliar with optomechanics, one of the main goals of cavity quantum optomechanics is to be able to control the motion of a mechanical oscillator using light. And a very nice example system to think about is a Fabry-Perot cavity, which has one large rigid input mirror and then one smaller back mirror that's sufficiently small and mechanically compliant that even the multiple reflections of light inside the cavity can modify its momentum. So then we can draw upon our tools of quantum optics and our ability to control light at a quantum level to then try and impart that control onto a mechanical oscillator. And it's a very exciting time to be in optomechanics at the moment because there's a wide range of different phenomena that are being able to be experimentally studied. And what's also exciting is there's also a very wide spectrum of different types of systems and experiments that are being pursued in parallel. For instance, there are efforts that use this favourable geometry with microscale mirrors attached to cantilever-type structures. There's devices that couple light and breathing modes in whispering gallery mode resonators. There's superconducting approaches where the resonance frequency of an LC circuit is modified by the position of a drum-like mechanical mode. There are photonic crystal approaches. There's also some very exciting levitation-based approaches, which is well represented here in the UK. And there are a number of reasons why all these different experiments and theoretical studies are being undertaken at the moment. And on the applied side of things, quantum optomechanics offers lots of promise for development in applied physics and development of new types of technologies, perhaps in part because it's a fully engineered quantum system. We can look at all the different types of materials and fabrication techniques available and then design a system that meets certain needs. For instance, optomechanical systems are currently being explored to exploit the long phonon lifetimes in some systems for quantum memory applications, where you can trap and essentially store quantum information that was initially in light into a phonon degree of freedom. These optomechanical systems can also be made to couple to a wide range of different forces. So they can be made very sensitive force sensors. They can also be made to couple to a wide range of different other physical systems, such as coupling to microwave fields and also coupling to optical fields. So the coherent conversion between microwave and optical fields is currently being pursued using optomechanics. And then on the more fundamental side, owing to the long lifetimes achievable and also the large masses and very interesting part of parameter space that's achievable with quantum optomechanics, one can think about how we can explore quantum mechanics on more macroscopic scales. And it's very interesting to empirically study the decoherence mechanisms that occur in this part of parameter space. And knowing more about quantum decoherence can shed light on the foundations of physics, and it can also help to improve quantum technologies. Decoherence, for instance, could set limitations to sensors or memories, so it's important to understand this. And then owing to this very large mass that's available, one can even think about studying the interplay between quantum mechanics and gravity. Okay, and with these in mind, and before I dive into the main topic today, I'd like to just briefly advertise some of the other directions that are being pursued in our team. One of the paths we're currently taking is towards the preparation of a mechanical superposition state. And to this end, one exciting step we've made is being able to experimentally see the first mechanical interference fringe pattern that was written into the thermal state of a mechanical membrane oscillator by using single photon counting. And then building upon some of the techniques developed here, we were then able to put together a theoretical proposal that uses a sequence of pulses and photon counting measurements in order to grow a mechanical superposition state where you can have a larger separation between your superposition components if you're willing to use a larger number of interactions and measurements. Some of the other areas that we've been pursuing is together with NPL in Teddington and Max Planck Erlangen, we've been pursuing some experiments studying techniques how to suppress backscattering in whispering gallery mode resonators. And then we've also been exploring theoretically entanglement between multiple mechanical modes. And we've been doing some works using pulsed interactions and studying Gaussian entanglement both between two oscillators and between two modes of a single oscillator, together with the Verhagen group in Amsterdam. And then we've also been looking at some photon counting based techniques, how to generate non-Gaussian entanglement between two mechanical oscillators, and then verify that entanglement using subsequent pulse measurements. So if you're interested in any of these directions that I've just highlighted, then do reach out to me either at the end of this talk or offline. I'll be very happy to discuss. And then today, what I'd like to focus on is some experiments we've been pursuing in whispering gallery mode microresonators. And here's a 3D artist's drawing of such a resonator that we've been using. And what you can see is a tapered optical fiber that's brought close to the surface of what we call a micro-rod resonator geometry, where between two valleys, there's a very smooth bulge, and light can circulate near the surface of this bulge in a very high Q factor whispering gallery mode. And as the light circulates, it interacts with high frequency sound waves. And we're very interested in the optomechanics between the light and these acoustic fields. And the mechanism by which we couple to these modes is backward Brillouin scattering. And now one of our current goals is to exploit this very strong form of optical nonlinearity between light and sound for quantum science and technology applications. And we pursue these experiments in close collaboration with 3 other experimental groups. The group of Pascal Delhaye in Max Planck Erlangen, and Jonathan Silver and NPL Teddington. And together with these 2 great guys and their teams, we study these types of whispering gallery mode resonators made from silica. And it's great discussions with these 2 teams about both the optical nonlinearities and Brillouin scattering present in these resonators. And then we're also exploring this geometry using also crystalline materials. And we've teamed up with Pinkoy Lam's team in Canberra in order to fabricate these crystalline devices. And I'll be describing more of that later. Okay, so the first part of today's talk will be Brillouin optomechanical strong coupling. That was an experiment that was performed in Oxford as we were transitioning to Imperial College London. Okay, now in quantum optics, strong coupling is really one of the key facets throughout quantum optics more broadly. So if you have an optical cavity or a cavity that confines some electromagnetic mode, and that field couples to a system of interest, it could be some kind of qubit, could be atoms, could be a mechanical oscillator, and that has some coupling rate, big G. And then your cavity has some decay rate, kappa, and your system of interest has some decay rate, gamma. And in order to be able to coherently control this degree of freedom, the system of interest, you want that your coupling rate G exceeds both kappa and gamma. And when you enter this regime, that's referred to as the strong coupling regime. And that allows some very interesting protocols to be pursued, also leads to qualitatively new phenomena. And strong coupling physics was really at the heart. It was very central to the great works by the Harosh team and the Wineland teams, looking at atoms coupling to microfields and trapped ion physics. And I've taken some other examples to highlight as well. This is the equally beautiful work by the Kimball team in Caltech in the early 90s, where they were able to see strong coupling between atoms inside an optical cavity. And when they entered the strong coupling regime, they see that the transmission spectrum through their cavity splits. And that's one of the signatures of strong coupling, where you see now the hybridization between these 2 different degrees of freedom and leading to this normal mode splitting. And there's been lots and lots of other examples of lovely strong coupling physics. And another example I'd like to highlight is strong coupling between qubits and microwave resonators, which is really very central to the great work in the superconducting circuit community. And within optomechanics, strong coupling has been studied. And I had a lot of fun during my PhD in Vienna, where we're involved in one of the earliest experiments that observed strong coupling. And in this experiment, what we're able to do is pump a Fabry-Perot cavity quite strongly, such that the coherent field inside the cavity enhances the interaction, giving a big G that exceeds both the optical decay rate and the mechanical damping rate. And then by doing interferometry of the field coming out of the cavity, we're able to see the normal mode splitting in the mechanical noise power spectra. And then also by varying the detuning of the input optical field, we're able to map out an avoided crossing, thus unambiguously demonstrating optomechanical strong coupling. And very quickly after this experiment, there was some lovely works that went one step further. And these experiments were done by John Teufel and colleagues in Boulder, and also Ewald Verhagen and colleagues. And there they're able to not only enter the strong coupling regime where G exceeds kappa and gamma, but also have a coupling rate that exceeds the rethermalization or decoherence rate of your mechanical oscillator. And this regime was then dubbed the quantum coherent coupling regime, owing to the fact that you can now control your mechanical system faster than it can undergo decoherence. And then since then, there hasn't been too many works in optomechanics that explore strong coupling. So we were quite keen to return to this types of physics. And at the same time, we're also very interested in putting together a set of desirable ingredients to cook up an optomechanics experiment, such that if we had this full set of ingredients, we'd be able to really exploit non-classical states of phononic degrees of freedom for quantum science and also fundamentals. And the ingredients that we would like to achieve is, firstly, we'd like to work with high mechanical frequency. And by that, I mean around 10 gigahertz, such that when this type of device is put in commercial cryogenics, it's in or very close to the ground state. As I've discussed, we'd also like to come back to strong optomechanical coupling and utilize the protocols and the physics that's achievable in that regime. And then one of the current hindrances in optomechanics at the moment is due to materials such as silicon or nanophotonic devices that have many interfaces. As you shine light on a device, it can give rise to heating. So we also want to circumvent that issue and explore systems that offer low optical absorption. Of course, it's obvious, but the next thing we want to have is low mechanical decoherence, such that if we create a non-classical state of a mechanical oscillator, it lives for long enough for it to be utilized. Then when we're probing this state, we want to be able to make measurements of the mechanical degree of freedom with high fidelity. And so that requires a good separability of the signal field from any pumped fields used. And it also requires a high measurement efficiency. And by that, I really mean how well you can measure the phonons or the mechanical state, kind of overall efficiency. And at present, although the field is making leaps and bounds, there's tremendous progress within optomechanics, simultaneously ticking all of these ingredients is not achieved by any single experiment. And that's something that I'm hoping to convince you today, that Brillouin optomechanics is an interesting route, a promising candidate path to being able to simultaneously meet all of these requirements. Okay, so within Brillouin optomechanics, you have an optical field that goes around your resonator, which is made of a solid material. And the atoms in the material are pulled towards regions of high electric field. And this is shown in this sketch where you have a higher density region of atoms here, a lower density region here. And this essentially helps to demonstrate the physics of electrostriction, where atoms are pulled towards regions of high intensity. And then so if you have an optical amplitude, you'll then get mechanical amplitude, and this is essentially akin to density that has twice the frequency to this field. And then the other side of this, essentially the same coin, is that now you have a periodically modulated refractive index, and that what that results in is the optical field being affected by the acoustic state, and that's essentially photoelasticity. So using electrostriction, we can manipulate the phonons with light, and then via elasticity, we can do a readout of this acoustic mode. And diving a little further into the system that we're currently studying, we have a pump coming in from the left into our whispering gallery mode micro-resonator. And the pump would circulate in the clockwise direction. And as it circulates, it interacts with a high frequency sound wave that counter-propagates to the pump. And that gives rise to backscattering of light at a quite similar frequency to the pump, but shifted by the acoustic frequency. And now, in order to get the strongest interaction possible with this type of regime, what we actually do is utilize two optical modes of the cavity. They're not spaced by the free spectral range, but rather they have a different transverse profile. And these are spaced by approximately the Brillouin shift. So then we have a pump mode, and typically in our experiments, that's the lower frequency mode of these pair of optical modes. And this pump mode gets resonantly enhanced by the presence of the cavity mode here. And then as it interacts with the acoustic field, that can give rise to anti-Stokes scattering, which is also resonantly enhanced by the second optical mode, provided that we have a small detuning between the mode and the Brillouin shift. And then when you're in this regime, where you have a fairly strong pump and you're driving the anti-Stokes interaction, because there's no optical mode out here, the Stokes scattering process is suppressed, and thus you're able to model this interaction as a light mechanics beam splitter interaction, much as you've seen in resolved sideband physics in, say, Fabry-Perot-based optomechanics. And now when Modasa sent the invitation for this talk, he asked for me to give a few words on state readout and state transfer. And I think it's best described here because a light mechanics beam splitter, as you drive a light mechanics beam splitter, what that's essentially doing is swapping the initial state in your anti-Stokes mode with the mechanical state. And when you pump this field, you initially have vacuum in your anti-Stokes. So by driving that interaction, you're trying to swap optical vacuum onto the mechanical mode, and concurrently, whatever you had onto the mechanics, you're trying to swap onto the anti-Stokes mode. So that's an equivalent picture of understanding laser cooling in this regime, where you're trying to drive the system towards the vacuum state. And then at the same time, if you have some interesting state that you want to read out, you can exploit this interaction to get your acoustic state onto the anti-Stokes field to then do a type of readout. And if you have a resolved sideband based experiment, then you can use this anti-Stokes or beam splitter type interaction that you get. And then if you have a system that's not in the resolved sideband regime, there are some pulsed approaches how to bring about an effective light mechanics beam splitter with some very nice works by the team Radim Philip and also James Bennett et al. Okay, now with the kind of drive frequencies and configuration described, the experimental setup that we used for this strong coupling experiment, in hindsight, is relatively simple. We use a telecoms wavelength fiber laser and do the entire experiment in fiber. And we pump our micro-rod resonator with the taper. And then we separate our signal, which is backscattered from the pump with a circulator. And then we mix that with another laser in order to do heterodyne detection of our signal field. And here's a microscope image of one of the first resonators that we were using in this strong coupling experiment. This was a resonator that was fabricated at the NPL, and it's a bit less than 1 millimeter in diameter, where you can see the optical bulge. Sorry, the bulge where the optical mode and acoustic mode lives in this image. Now for the telecoms wavelength and using silica, that gives a Brillouin shift or an acoustic frequency of about 11 gigahertz. So that's nicely ticking our first wish list on the first item on the wish list for the ingredients. And then at room temperature, we observed that this acoustic mode has a line width of about 20 megahertz. And the optical cavity that we were using, unfortunately, it had degraded a little bit with some dust. It was initially order 10 to the 9, but when we did the experiment, it was order 10 to the 7. That had a line width of around 3 megahertz. And so what we need to do is be able to achieve a coupling that both exceeds the mechanical decay rate and the optical decay rate. So let's now look at the Heterodyne results. When we turn on our pump and just have a weak pump initially, and you see in the Heterodyne, the noise power spectrum, you see a nice Lorentzian appearing at the frequency you expect. And that makes very good sense because we've got a damped, stochastically driven mechanical oscillator, and we're weakly transducing that acoustic mode onto our anti-Stokes mode. And then when you start to turn up the power, we can see that firstly our signal grows, but excitingly this second peak starts to appear. And this is the kind of first signature of starting to enter the strong coupling regime. And then as you pump even more strongly, we can see that there's a wider splitting between these two peaks, and it looks nice and symmetric in this plot. Pumping even more strongly, we can see that there's now a bit more power density in this left part of the noise power spectrum. And then what we did is we're able to record many of these spectra and put them all together into a color map plot. And what I'd also like to draw your attention to on this slide before I move on is note that as the coupling rate that we estimate we achieved goes up in these four traces, the detuning is also changing. And the detuning is going down because of two reasons. One is that when you have light inside a silica resonator, the optical Kerr effect slightly shifts where these resonances lie. So that's slightly changing the detuning. And then a very similar form of nonlinearity is the photothermal effect, which is also shifting the spacing between these two optical resonances. Unfortunately for us, we're able to find a pair of modes that started off with a finite detuning, such that when we were able to increase the power, that detuning went through a zero crossing as we entered the strong coupling regime. So we're able to see this nice symmetric noise power spectrum and be in the strong coupling regime for very small detuning. So let's now look at this data further. All the noise power spectra that I showed on the previous slide are now slices in this plot. So as you change your input pump power, here we've plotted it in terms of the intracavity power, which just takes quite high values. And on this axis on the top here, you can see that the detuning drops and even goes through this zero crossing at this point. So when we're changing the input pump power, we're not only, when we're increasing that, we're not only increasing the coupling between the light and sound, but we're also changing the detuning. And then if you model such a coupled oscillator system and you have no detuning, then that's a classic undergraduate textbook problem. It's really, really fun problem to solve. And if you have two masses on springs, then initially these masses on springs set the frequencies the same, they're degenerate. Then when you're able to couple them together more strongly than the friction present in the system, that degeneracy lifts and you see these two modes appear. And now in practice, we didn't see that in our experiment because we don't have zero detuning. Our detuning is also changing. So with this experiment, we're not only increasing G, we're changing the detuning, and that allowed us to simultaneously map out this avoided crossing feature. So we're very excited about these results. So this demonstration of Brillouin optomechanical strong coupling, we're able to enter the strong coupling regime for quite modest input powers. And we're then able to go quite deeply into the strong coupling regime where we were limited by powers we had available and also the stability of our locking of the pump. And before you pump the system, the kind of underlying optomechanical coupling rate in this case is 400 hertz, but we're then, by pumping the system, able to get the coupling rate up to border 40 megahertz, thus far exceeding the mechanical and optical decay rates by more than a factor of 3. And having strong coupling in optomechanics is interesting because it's essentially rapidly driving a swap between light and sound. And so that makes a useful ingredient if you want to create a quantum memory of storing quantum information from photons in phonons. So that result was published a couple of years ago now. And I do also encourage you to see related work by Kim, Taylor, and Ball, where they're also able to observe Brillouin optomechanical strong coupling, albeit to the forward scattering mode, and that was published later the same year. Okay, now I'd like to move on to the second part of today's talk, and that is essentially very similar physics, but we'll now be pumping it more weakly. And we'll also be changing the way that we do our measurements in order to herald some different operations that exploit these anti-Stokes and Stokes physics. In particular, I'd like to describe how we can add or subtract a single phonon to initial thermal states of this acoustic mode. And I'd like to start off this section of the talk with a question. If I have a single mode thermal state of a harmonic oscillator, and I have the ability to add or subtract a single quanta of that mode, what happens? Mordasa, I'd be very grateful if you could help me spot if anyone has any guesses or questions.
Everyone's very thinking right now.
So you may expect that if you have a big thermal state, then adding or subtracting a single quanta might not do much. And indeed, that's what I was thinking when I first heard about these types of directions. But of course, it has a dramatic effect. Otherwise, I wouldn't be showing this slide. And very interestingly, if you have a single mode thermal state of mean occupation n bar, and you're able to subtract a single quanta from that thermal state, then the mean occupation actually doubles. It goes up to 2n bar. And then similarly for addition, it approximately doubles, but you get this very interesting +1 effect. And this quite counterintuitive result, when you first see it, has been experimentally observed, and it's been quite well studied in optics, in particular by the Bellini group in Italy. And one very nice example that I'd like to quickly describe is that the Bellini group were able to make a thermal state, single mode thermal state of light. They put that up to a weakly reflecting beam splitter. And then when they detected a single photon at the reflected port of the beam splitter, they know that they've taken out a single photon of this thermal mode. And then by essentially doing Heterodyne tomography of the output, they can then characterize what happens to the state when you do that single phonon subtraction operation. And indeed, they saw that their occupation, which started off quite low in the thermal state they made, did approximately double by that procedure. And the reason why it doubles is that you're shifting your distribution in the number basis down by 1 when you're doing the subtraction. And it's also a non-unitary process. By getting that click, you're actually learning information about the state that's gone into the operation. And so you must update your state with that knowledge that you've gained by using the measurement. And so the Bayesian inference part of the process turns out to be quite significant, resulting in the doubling of the occupation. And then partly inspired by these works in optics, the latter stages of my PhD, together with Markus Aspelmeyer and Young-Shik Kim, we were cooking up how you can add or subtract single phonons in optomechanics, essentially by driving the red or the blue sideband and then getting a single photon click, thus heralding single phonon addition or subtraction. And we had some ideas about how that can be used for state preparation, and also how it could be performed simultaneously. So you can even do a superposition of addition and subtraction. And we're quite unaware, but at that time when we were working on the theory, there were some experiments pursuing essentially the same recipe that we had in mind. And they were looking at these types of anti-Stokes and Stokes interactions between light and high frequency vibrations inside a diamond crystal. And very excitingly, we were able to create non-classical states between light and these vibrations in the diamond, and also even entangle two diamonds. So fantastic work, really some of the first pioneering experiments in optomechanics demonstrating non-classical states of motion. And then building on these ingredients, the Vienna-Delft collaboration was able to go even one step further, go a bit beyond these experiments with the diamond, and also bring these experiments down to a lower frequency regime and look at similar types of non-classicality between light and mechanical modes inside a photonic crystal structure. And it's a very rich space, so there's much to explore here. So we were keen to get back into this area experimentally. And at the same time, we've got lots of other items on our ingredients wish list to tick. In particular, we'd like to be able to have an optomechanical system that has really excellent coherence properties. And one promising way that we think may work is to use, again, these whispering gallery mode geometries and looking at Brillouin scattering in these, but now using crystalline materials. And so we've teamed up with the group in ANU, and we've been working very closely with Yuri Januzek and Bhavin Shajilal. And these guys have been making some really lovely crystalline whispering gallery mode devices using a diamond nanolathe technique. And we've done a couple of experiments with these new devices at room temperature that I'd like to now describe. So focusing on this panel down here to start, what we have is essentially the same type of physics that was shown in the strong coupling section, where you now drive a optical mode that's at the lower frequency mode of a pair of optical modes spaced by the Brillouin shift. And that brings this anti-Stokes scattering into resonance. But now what we do is we select out this backscattered anti-Stokes field and filter that spectrally. And then we detect single photons here. And then when we've detected a single photon, we know that we must have subtracted a single phonon. We can also do you can flip things around, where if you drive the upper frequency mode of the pair and detect a downshifted single photon, then upon getting that click event, seeing a single photon here, we know that we must have added a single phonon to our mechanical mode. And so we're able to build upon the strong coupling work that we'd been doing, but now we're using much weaker pumps because we want the probability of multiple photon scattering to be low, because we want to work at the single phonon level regime. And so we pump our micro-resonator as before, our signal field comes back out, and then we now separate that and we pass that through a filter to block any residual pump that came through. And then that goes on to a single photon detector. And now when that photon detector goes click, that heralds that triggers a heterodyne interferometry process. And we can then record the heterodyne time trace about the time that we get click. And here's an example such trace. And again, let me reiterate that we're working in the weak coupling regime. So what we see is essentially noise. Indeed, it's mostly vacuum noise, or a lot of it is vacuum noise, which is shown by this gray region. We're transducing a little bit of the acoustic thermal state onto the field, but at the trigger event, you can see that there's something interesting happening here. Let's dive into that a bit further. And what I'm plotting here is now the variance of the traces. And let's focus on this upper panel first. So you can see in the gray line, this is the optical vacuum that we measure in the experiment with time about the click event. And we've normalized that so in this work, so it takes a value of 1/2. And then now we're weakly coupling to our acoustic mode. And so away from the click time, you can see that there's some extra noise on our signal field, and that corresponds to the thermal state being partially mapped onto the anti-Stokes field. And then now, excitingly, at the time of the click event, you can see that this noise goes up. And indeed, it goes up by just the right amount that it's essentially a near perfect doubling of the acoustic occupation. And it's not perfect because we have some dark counts in our detector. And we also have some filtering that goes on that we haven't fully taken into account, but we believe we understand this small discrepancy. And so the acoustic state is taken out of equilibrium by this measurement process. And initially at room temperature, it has an occupation more than 700, And then by doing this subtraction or addition process, we can see that the occupation doubles. And we're excited by this result because it's the first, to the best of our knowledge, the first study that's looking at this doubling of a single mode bosonic system outside of light. And since we submitted that work, we've been studying it further. And in particular, we've been working on making new devices, improving our setup, and improving the overall readout efficiency to most efficiently, or as efficiently as possible, get the state of the mechanical motion that we're interested in to our detector for state verification. And right now, we can do that with an overall efficiency from phonons to detected photons in our heterodyne detector of about 1% efficiency. So there's still some ways to go for it to be improved. And within optomechanics, the field moves rapidly, so I'm sure that will be superseded quickly. But with that performance, we can already start to see some new qualitative phenomena building upon that last work. And so now what we were then able to do is not only look at single phonon addition subtraction, but by having two detectors and looking at coincidence clicks, you can then subtract two or add two phonons to the oscillator. And with the higher efficiency readout from mechanical mode to optics, we can then start to map out the phase space of the mechanical state. And so that's shown here. And our initial state, before we do any additional or subtraction operations, is this Gaussian state. We're in thermal equilibrium. All makes sense. And then when you do single phonon subtraction, you're taking the system out of equilibrium, and it's also a non-Gaussian operation that you're applying as it involves single photon counting. And so the state it produces is actually a non-Gaussian state in phase space that has this ring-like structure. And so with the efficiency that we're able to achieve in this experiment, we're able to advance the state of the art in optomechanics-based tomography of mechanical degrees of freedom using light. And as I said, I think that advancement will be very quickly superseded by near future improvements within the field. But nonetheless, it was sufficient for us to see this non-Gaussianity and see that ring-like structure, which grows when you do two phonon subtraction. And what I'd also like to highlight here is that note that these axes of the phase space that we're plotting is the units of the axis is in mechanical 0-point fluctuations. So this would be from here to here is 20, 0 point, another 20, 0 point. So you can really start to see we're honing in on the ability to see some features at the quantum level. And here's photographs of the first four joint first authors in this work that came out late last year: Georg Enzian, Lars Freisum, John Price, who has his Viva this coming Monday. Good luck, John. And Andreas Vella. And looking at the data further, here's a plot now of the variance that we measured as a function of time. You can see now with the much higher efficiency readout, we've got much greater signal to optical vacuum noise. And this plot essentially shows that for single phonon subtraction, you can nicely see the doubling of the mean occupation. And then for two phonon subtraction, the mean occupation triples. And so we observe that well, which matches a theory, which also captures this the dynamics as the system goes back into equilibrium. We can also look at our data in time and see how it goes from a Gaussian, if you're to take a slice through here to this non-Gaussian distribution, which is plotted here. I hope you can see that a bit more clearly, where the blue is our initial state, and then the green is the distribution of a mechanical quadrature that you'd get after a single phonon subtraction and then two phonon subtraction process. So that work was published late last year. Now, I also encourage you to look at some related work that was done by the Safavi Naini team in Caltech, where they were also able to see some of these types of effects in a photonic crystal structure. And now, starting to wrap up, let's come back to these ingredients. What have we achieved, and what's left to go? And we've been making progress. So we're confident that by exploiting the state-of-the-art optical materials such as silica or fluorides in a bulk, you can circumvent some of the issues of heating and absorption. So we're tentatively giving that a tick. We're excited by the combination of having high frequency and strong optomechanical coupling. So those have been demonstrated. In backward Brillouin scattering, your signal comes out in a different direction from your pump. So separability is made much easier in our experiment. And then we've got two challenges that we're currently working on. One is that our mechanical coherence properties can be improved by operating at cryogenic temperatures. So we're currently gearing up towards doing these types of experiments. And once we're at cryogenic temperature, the mechanical cooperativity should be much higher, allowing a more efficient state transfer from the acoustic mode to the optical field, which will allow an overall much higher measurement efficiency of the mechanical state. So there's some works in progress within our team. And I'd like to thank very much all the funders that support our team and our activities. Do reach out to me if you're interested in PhD or postdoc positions. And thank you very much, everyone, for your attention today. Be very happy to take any questions.
Thank you, Michael, for a really informative talk and really clear, as always. Really exciting work. Thank you once again.
Pleasure, Modesta.
So I'll just, of course, open it up to anyone who has questions. If you can raise your hands, you can, of course, type in the chat. I'll bring that forward. And if there's any questions from YouTube, Clara, if you can send that to us. So we have a question from Johan.
Hi. Thanks for a great talk. Could you be so kind to go back to when you were beginning to start with talking about the backwards Brillouin scattering and how that were related into how you got that to be, to be this beam splitter interaction.
Yeah, okay, great. So the Brillouin scattering is an interaction between a pump field, which is shown here going clockwise around the structure, an acoustic field, which is counter-propagating, and the new field that you generate, which also counter-propagates. And that's a three-wave mixing process. So the full Hamiltonian, I might get the daggers wrong, but it's something like A pump, A anti-Stokes dagger, B plus Hermitian conjugate. So it's a three-wave mixing process between two optical fields and one acoustic field. So it's a cubic interaction, much like radiation pressure. A dagger A couples to B plus B dagger. That's also cubic, but this is fundamentally different to radiation pressure force because it involves two optical fields and a three-wave mixing process. So when you pump one of these modes strongly, you can do the standard procedure of going from an annihilation operator to a complex number and arrive at a Hamiltonian that looks like the beam splitter Hamiltonian. And more physically, what this is corresponding to is that we've got a strong pump and we're creating anti-Stokes light. We're not seeing any Stokes light, so we model it as this light mechanics beam splitter. Was that helpful, Johan?
Yeah, but why don't you see any anti-Stokes?
Ah, cool. Yeah, we don't see any Stokes scattering. So there's no sideband over here.
Yeah.
Because there's no density of states in the resonator. So there's no optical resonator mode here that supports the Stokes light. So that gets destructively interfered. So light can only exist where there's an optical density of states. So that is one of the advantages of using these two optical modes.
Okay, so all right. So and is that set by the free spectral range of this resonator? Or
yes.
is
So no, good question. So for the diameters of these devices, the free spectral range is about 100 gigahertz. So the free spectral range is much, much bigger than the Brillouin shift. And if the free spectral range was equal to the Brillouin shift, then indeed you would have another cavity mode down here. And then you would get both Stokes and anti-Stokes processes. And the Stokes interaction will eventually win because that's a gain process. So that will run away and you'll see Brillouin lasing. But if you want to just see anti-Stokes, then if you have a much smaller resonator, these micro-resonators are really perfect for these types of experiments, then if you can find a pair of modes that have this spacing, then you're in business. And the slight disadvantage is we have to search through many, many optical modes to find candidate pairs that have that right spacing. Great questions.
Yeah, so that means that if you would have the Stokes process if you would have pumped at the right one of these.
Absolutely, exactly. And the Stokes process is what's used for addition. If I pump here instead, and then I'm creating Stokes light, then my Hamiltonian is now a light mechanics two-mode squeezer instead of a light mechanics beam splitter. So that will look like A Stokes B plus A Stokes dagger B dagger. So thus, if I create a Stokes photon, I've created a phonon in that mode.
That's very interesting.
Good questions. Thanks for the questions, Johan.
Yeah.
There's a question by Edward.
Hello, thanks for that really nice talk, Mike. I had a question about your addition and subtraction experiment. So,
yeah,
you have these very nice features where the variance increases, but it then seems as though your high variance state doesn't persist for very long.
Yes.
What's that time scale?
Yes. Okay. So when you get the click, you take the state out of equilibrium, and then the state will then we're not doing anything more, so it will then start to return to thermal equilibrium. And what's dictating this decay is essentially the mechanical decay rate, which for these room temperature experiments, in the strong coupling work, it was 20 megahertz. But then going to the silica resonators, that was of order, I think 5 megahertz or so. I'll have to check that number. So that's why you can see it's just the decay of the oscillator back into thermal equilibrium is giving us about 20 nanoseconds or so lifetime in order to see this at room temperature.
Okay, so it is simply the mechanical decay rate. The 20 nanoseconds is 50 megahertz.
We've done a very careful analysis that gave us this curve. The optical decay does play a role in this shape, but for our experimental parameters, it's mainly dominated by the mechanical lifetime.
Okay, thank you.
Yeah. And then at cryogenic temperature with crystalline materials, because you've got this lovely long-range order, or the atoms are all locked in the lattice, the atoms don't jump around, which is one of the main decay channels in amorphous materials. And so there we're very hopeful that in this geometry for these materials, you'll get a much longer lifetime and be able to really utilize these out of equilibrium states.
Thank you.
Thank you, Edward, for that question. I'm just conscious of time. I think we're slightly out of questions. So if it's okay, we'll wrap up here and thank Michael again for a really great talk and wonderful science that we get to show.
Oh, thanks for having me, Mordasa and Unicorn team. Really enjoyed it.
Great. So before everyone leaves, I just want to quickly share my screen and show you our next block. You can see that. So we'll be joined next week by Andre and Nicola, showcasing some of the excellent work in optomechanics and levitated optomechanics specifically. So I hope you can join us then. And that will also be 2 p.m. GMT again next Wednesday. So until then, thank you once again, Michael, and thank you everyone for joining us. Have a great week. Right.
Thank you, everyone. Take care. Bye-bye.